Welcome to CE 405 Environmental Engineering 1 Module 6 Part 3. In the previous session, I had already given a question for solving the pipe network analysis by using Hardy-Cross method. This is the first question which is drawn here. In the question itself, the discharge through every junction, that is discharge entering into every junction is given. That is, here it is 50 liters per second. In the second junction it is also 50 liters per second. In the last, then 75 liters per second, then 25 liters per second leaving from this junction, and also the constant K is also given for each individual pipeline. Here we have to give names for these pipes, that is A, B, C, D. Here 5 pipelines are there, AB, BC, CD, BA and DD. These are the 5 pipelines for which the K value is given. The first rule you have to obey for solving this pipe network analysis by using Hardy-Cross method is that all the discharge coming into a junction should be equal to all the discharge leaving from that junction. That is, in the first junction A, that is junction A, the flow coming into that junction is 50 liters per second. That should be equal to the flow leaving from that junction. Here 2 pipelines are there, that is AB and AD, starting from A. So we have to divide this 50 liters per second flow into 2 pipelines. I am going to divide it by 25 liters per second plus 25 liters per second. That is like this, 25 liters per second, 25 liters per second. That is, the flow entering into a junction should be equal to the flow leaving from that junction. Next we will move on to the next junction, that is junction B. In that junction, 25 liters per second flow is going into junction B, and another 50 liters per second flow is also entering in that junction B. So the total flow entering in that junction is 50 plus 20, that is 70 liters per second. The flow leaving from that junction should be through the pipe BD and pipe BC. Here now I am going to divide it by 25 liters per second and 50 liters per second. Sorry, this is 25, not 20. So the flow leaving from that junction will be 50 plus 25. So the rule is clear. Then the next junction, that is junction C. Junction C, the flow entering into that junction is 50 liters per second, but the flow leaving from that junction is 75 liters per second. So we have to get a more flow of 25 liters per second through the pipeline DC. So we can assume that here the flow should be like this, that is 25 liters per second. That is 50 liters per second flow is arriving at junction C, and another 25 liters per second is also arriving at junction C, and a total of 75 liters per second is leaving from that junction. So here also the rule is clear. Then the next junction, that is junction D. For junction D, the flow 25 liters per second is coming into junction D, and also these 25 liters also coming into the junction D. So a total discharge of total flow of 25 plus 25 is coming into the junction D. Here the 25 liters per second is leaving externally, that is outside the network through some other pipelines or some other pipe network. Is leaving from that junction. So 25 is leaving, the rest is 25, that is leaving through the pipeline DC. So it is equal to 25 plus 25. So the rule is cleared for junction D also. This is the flow pattern that we are assuming to solve the pipe network system shown in figure by using Hardy-Cross method. You can assume this as 20-30 or 10-40, any value, that is the total should be equal to 50 liters per second. This is up to you. But by assuming this kind of discharge, then the iterations or the correction steps will be more. So you have to minimize the correction step. So according to that you have to divide. Anyway, for examination purpose, 2 corrections are enough. So you have to, you can assume any value that should be, the total should be equal to the given discharge. That is the only point you have to take care of. The first step of Hardy-Cross method is over for this problem, that is assuming the flow through each pipeline. Next we have to calculate the head loss for this pipe network. The equation for head loss is HL is equal to K into QA raised to X. This K will depend upon what equation we are using for calculating head loss. There are 3 equations for calculating the head loss in a pipe network analysis. That is, first one is Hazen-Williams formula, second one is Manning's formula, third one is Darcy-Weisbach equation. Here in the question itself it is told that the flow is turbulent and the pipe is rough. So we have to use the Manning's formula. For Manning's formula, X will be equal to 2. For each equation, that is these 3 equations, Hazen-Williams formula, Manning's formula and Darcy-Weisbach equation, this K value will be different. For this question, the K value is already given. So we need not to calculate the K value for this pipe network analysis. For next example, we have to calculate the K value. If the K value is given in the question, you don't want to worry about that. If it is not given, then you have to calculate this K value. You have to convert that equation, that is Hazen-Williams formula or Manning's formula or Darcy-Weisbach equation, in this particular format. Then you will get the equation for K. And calculate the K value for each pipeline in that pipe network. Here it is also already given, so you don't want to take care of that K value in this question. So this is the equation for head loss. Then we will move on to the pipe network analysis, that is Hardy-Cross method. Here is the tabular column that you should complete it for the analysis purpose. The first column is the pipe, then second column is the assumed flows, that is the 25, 25, 50 that we are already assumed for the pipe network system given. And then K value, it is also given. Then you have to calculate the HL value, that is the equation here. X will be equal to 2. That is HL is equal to K QA raised to 2. Then the equation is mode of HL by QA. Then the last column is corrected discharge through each pipeline in that network. Then we have to calculate the correction factor. That is the correction for the first correction, that is delta 1, by using the equation minus sigma HL divided by x into sigma mod of HL by QA. This is the basic procedure. Then we will move on to our problem. Pipes are, first we have to consider the first loop. The first loop is A, B, D, A. This is the first loop. So the pipelines are first AB, then BD, then DA. These three pipelines are for the first loop. And the assumed flow through that first loop pipes are given in the column. That is, for AB it is 25, that is clockwise direction. The flow is in clockwise direction, so that the sign convention is positive. Then next BD, it is also in clockwise direction, 25 liters per second, also positive. Then next is DA, not AD, it is DA. Here the flow is in anti-clockwise direction, so you have to give a minus sign, that is minus 25. And the K value is already given. For AB it is 2, for BD it is 1, and for DA it is 2. Then calculate the head loss value using the equation K into QA raised to 2. QA is already we assumed and K value is already given. Then calculate the values for the head loss. Then here we have to calculate sigma HL. Then next column is mod of HL by QA. That also you can calculate. HL is also already calculated. QA is given in the second column. Then this also you have to calculate sigma mod of HL by QA. Then substituting in equation for the correction, that is the first correction, delta 1 minus sigma HL divided by x into sigma HL by QA. These are the values. Sigma HL is here 625 and mod of HL by QA is 125 and x value is 2. Then we will get a correction as minus 2.5. Then you have to add this correction to the assumed flows. Then only you get the corrected Q for the after the first correction. Here you have to consider the common pipeline for the two loops. Here two loops are there, that is A, B, D, A, and next is what? B, C, D, B. Here the pipeline BD is common for two loops. So you have to give both corrections to that pipeline. Correction for loop 1 should be given to that pipeline and the correction for the second loop also given to that pipeline. So you have to calculate the corrected flow after the second loop calculation. Then only you get the value of the pipe BD. You can calculate for AB and DA. Here it is 25 plus minus 2.5, that is equal to 22.5. Here also it is minus 25 plus minus 2.5, that is minus 27.5. This is the corrected flow for the pipes AB and DA. Then we will move on to the next loop, that is BCDB. For the second loop, the pipelines are BC, CD and DB, and here is the assumed flow through that pipeline, that is through BC it is 50 liters per second, for CD it is 25 liters per second and it is anti-clockwise, so a minus sign is there, and also for dB it is 25 liters per second anti-clockwise, so we are giving a minus sign. The K value for these pipelines are 4 for BC, and then CD the 3, dB 1. Then you have to calculate the head loss for these pipelines, that is HL is equal to K into QA raised to 2. Then we will get a value of 10,000 minus 1,875 minus 625. Then you have to calculate the mod of HL by QA, and we get these values, and you have to find the sigma HL value, that is 7500. Then sigma mod of HL by QA, that is 300. Putting these values in the equation for the first correction of second loop. First correction of second loop. That is, we are denoting this correction as delta 1 dash. That is sigma minus sigma HL divided by x into sigma mod of HL by QA, and we get a value of minus 12.5. Then we have to give the correction to these flows. That is, dB is the common pipe, so the rest we can apply directly. That is 50 plus minus 12.5, and then minus 25 plus minus 12.5, and then the common pipe dB. Here two corrections are there. One is delta 1 dash, that is minus 12.5, and the other one is our value was minus 2.5, that was delta 1. You have to apply these two corrections to the common pipe dB. Here the value is minus 25 plus minus 12.5. Here the correction calculated for the pipe as BD. Here the pipe is dB. So you have to change the sign for this correction. That is plus 2.5. This is the corrected flow for the common pipe dB. Here also you can calculate the corrected flow for the pipeline dB. That is, here it is 25 plus minus 2.5 plus, here the value is minus 12.5, but the pipe is dB. Here the pipe is BD. So you have to change the sign, that is plus 12.5. This is the corrected flow for the common pipe. These two values should be equal and opposite. You can see both the values are equal and opposite. Here the corrected flow for BC is 37.5, and the second pipeline CD it is minus 37.5, and for the common pipe it is here it is minus 35, and here it is plus 35 is equal to plus 35. This is a check, that is all the calculations are correct or not. This is the first iteration, first correction for the pipe network. Then you have to complete the second correction also by selecting these Q values, these corrected Q values as the assumed flow in this column. Then you can apply same procedure, you can use the same procedure, same calculation method to complete the calculations. Let us start the second correction for the same pipe network. That is, the first loop is ABC, AB, DA. First pipe AB, BD, then DA. The corrected flows in the first correction is taken as the assumed flows in the second correction. That is 22.5, 35 and minus 27.5. Then K value already given. Calculate head flows using the equation K HL is equal to K into QA raised to 2. These values are calculated. Then the mod of HL by QA that we calculate. Then sigma of HL, head loss is calculated. Sigma mod of HL by QA is also calculated. Putting these values in the correction equation, that is delta is equal to minus sigma HL divided by X into sigma mod of HL by QA, we get a second correction as minus 2.7. Add these corrections to the assumed flow in the column, that is 22.5 plus minus 2.7, that is 22.5 minus 2.7, that is 19.8. Then 35 is a common pipe, so you have to consider the second loop also, then only you can calculate the flow correction for the common pipe BD. You can calculate the flow correction for directly for the pipe DA, that is the already assumed flow is minus 27.5. You have to add this value, that is the second correction minus 2.7 to this value, then you get a value as minus 30.2. Then considering the second loop, that is BCDB, BC, CD and the common pipe DB. The assumed flows are the corrected flows in the first correction, that is 37.5, minus 37.5 and minus 35. K values already given 431, and calculate the value of HL, that is K into QA raised to 2. All the values are calculated. Then sigma HL is also calculated. Then HL by QA, mode of HL by QA is calculated by using the equation. Then sigma mod of HL by QA is calculated and the value is 297.5. Putting these values in the correction equation delta, we get a second correction for the second loop, that is delta 2 dash as minus 0.3. Then you have to add this correction to the assumed flow, that is 37.5 minus 0.3 for the pipe BC, that is 37.2. Then minus 37.5 minus 0.3, that is minus 37.8. Then DB is the common pipe. You have to apply both corrections to that pipe. Then it is minus 35 minus 0.3. Here you get minus 2.7. So you have to add plus 2.7 for the pipe DB, because this is the correction for the pipe BD. So you have to add plus 2.7, then you get a value as minus 32.6. And here also you have to add the correction for the common pipe, that is 35 minus 2.7. Here the value is minus 0.3, then you have to add plus 0.3 in the first loop for second correction. And you get a value as plus 32.6. These are equal but opposite. This is the main procedure for the Hardy-Cross method in the pipe network analysis. By doing this, you get a corrected flow. When the correction calculated is decreasing below 0, you can stop the correction. For examination purpose, only 2 corrections you have to calculate, and the figure also you have to draw. That is the original figure you have to draw, and mark all the corrected flows in that diagram. This was our pipe network that is given for solving and finding the discharge through each pipeline. Then you have to mark all the corrected flows in this pipe network system. For AB, the corrected value is, for AB it is 19.8, and for BD it is 32.6, and for DA it is minus 27.5. Then the second loop, that is for BC, it is 37.2, and for CD it is minus 37.8, and the common pipe it is the 32.6. Likewise, you have to draw the figure again and put all the corrected flows in this pipe network system. Then only the analysis part will be completed. So I hope you understood the problem. Take care and refer the textbook also. Thank you for listening. Bye-bye.